In this module, we're talking about crystal structure, the structure of solids. So a solid can be either a crystalline solid or an amorphous solid, basically. In a crystalline solid, there's a long-range order at the atomic level, and that comes from what's called a unit cell, a pattern that's repeated in 3 dimensions. In an amorphous solid, there is no pattern. There's no long-range order at all. An example of a crystalline solid would be a diamond. An amorphous solid would be like coal. They're both made of carbon, but very different from each other. There's that unit cell that gives a crystalline solid its long-range order. There's 7 types of these: simple cubic, tetragonal, orthorhombic, rhombohedral, monoclinic, triclinic, and hexagonal. We will only speak about simple cubic in this course. These are just some examples of crystalline solids, and one of the interesting things I think is that you can see the patterns that exist at the atomic level in the macroscopic structure, in the large scale structure of these substances. Diamond, it's just carbon, but it definitely has a pattern to it that you can see. Sodium chloride, table salt. If you see a big crystal of sodium chloride, there's definitely structure to it. You can see the structure, and that comes from the underlying arrangement of the atoms in unit cells. Same thing with ice from water. Now, this unit cell, this is the simplest possible one here. But if this were the atoms of a solid, a crystalline solid, all attached to each other, these would be the attractions, the bonds. It depends what kind of solid it is between the atoms making up the solid. And the unit cell would be the simplest pattern that you can get this structure from. And it would look, in this case, it would look like this, a cube. So if you take this cube and repeat it up, down, front, back, sideways, you would get the long-range order. That's a unit cell. Now, we're going to talk about 3 different kinds of unit cell. Primitive cubic, you'll also hear me call primitive cubic a simple cubic unit cell. So they both mean the same thing, primitive and simple cubic. Body-centered cubic and face-centered cubic. What they are is a simple cubic unit cell. It just has 1 atom on each corner of the unit cell, like this. These are the same. A body-centered cubic, it's just what it says. There's an atom right in the middle of the body of the unit cell, surrounded by the corners. It also has 8 corners, each with an atom on it, with 1 in the middle. Now in a face-centered cubic unit cell, we also have the 8 corners with atoms on them, and on each of the 6 faces, there's nothing in the middle here now. This one's not there anymore over here. There's just an atom here, on the top face, the bottom face, the side faces, the front and the back face. That's face-centered cubic. Now, those pictures that you just saw, the entire atom did not belong to that 1 unit cell. It's shared with other unit cells. Like this is what it might look like a unit cell, a simple cubic unit cell, a primitive cubic or simple cubic. There's just really part of that atom on each of the corners that's actually in the unit cell. The rest of that atom, it's in other unit cells that are touching this unit cell. So if an atom's on a corner of a unit cell, like this one, then it's shared with 7 other unit cells for a total of 8 unit cells. So to see that, this outlined in red would be 1 unit cell. This would be another, and then there's 4 on the bottom too. Each of these has 1/8 of this atom in it. So this atom is shared between 8 unit cells, or another way of saying that is each unit cell has 1/8 of that atom. Now, if an atom is on a face, like in face-centered cubic unit cells, then it's just shared between 2 unit cells. And so that 1 unit cell gets 1/2 of that atom. And so what we say is that in a face, for example, a face-centered cubic unit cell, because there are 6 faces and each has 1/2 of an atom, 6 times 1/2 is 3 atoms from the faces, plus there are there's 1/8 of an atom on each of 8 corners. 8 times 1/8 is 1, so 3 plus 1 is, there's actually 4 atoms per unit cell in face-centered cubic. So let's look at that. So this is what a simple cubic unit cell would look like. There's 1/8 of an atom on each corner, times 8 corners is 1 atom per unit cell. These are important numbers to remember. In a body-centered cubic, there's also 1/8 of an atom on each corner, times 8 corners is 1 atom on the corners, plus we have that 1 in the middle, is 2 atoms per unit cell. And we just saw how the face-centered cubic unit cell has 4 atoms per unit cell. Now, this is some of the geometry. What this does for you is it relates the length of an edge of the unit cell to the atomic radius. So let's start out with the simple cubic unit cell. In a simple cubic, the atoms on the corners are touching each other. So from one corner to the end of that atom is 1/2 of the length of the edge. And then we have another length here. So this is R and another R. So A is equal to 2R. A is what I'm going to use to signify the length of an edge of the unit cell. So, and you should remember the bottom lines here. A equals something with R. So remember, when the simple cubic unit cell, the edge length is equal to 2 times the atomic radius. Now, in a body-centered cubic unit cell, we have to do a little bit of geometry. Now, because this atom in the middle here is pushing the corner atoms apart, they're not touching each other anymore, so we can't say A equals 2R. What we have to do is we have to set up 2 right triangles. The first one would be on one of the faces. And so this is a right triangle. Pythagorean theorem says that B squared, which is the diagonal length, is equal to A squared plus A squared. Each of these lengths is A, or 2A squared. Now here, this other triangle we're going to make, C, it goes from the bottom left corner through the middle to the back top right corner, front to the back. And that distance would be, there's an R here, plus there's 2 R's going through that one atom, plus another R. There's 4 R's there. And if we set up a triangle with C here, the same B, and an A, we can say that, this is a right triangle also. We can say that C squared is equal to A squared plus B squared. But we know that B squared is equal to 2A squared, so C squared is really equal to 3A squared. Well, taking the square root of both sides, we get C equals the square root of 3 times A. And we also know that C is equal to 4R. So what we get is A is equal to 4R over the square root of 3. So this is what you remember. You don't have to remember the derivation necessarily. Sometimes it's easier to remember the derivation than the actual formula. But yeah, either way is okay. This is what you guys are going to use for the body-centered cubic unit cell. For the face-centered cubic unit cell, we just, again, these face atoms are pushing the corner atoms apart so they can't touch each other. But what we can say is, because the distance from, say, one corner diagonally across to the other is 1R plus 2 R's through the middle atom, and another R is 4 R's here, we can say B is equal to 4R. That's this line right here. We can also set up a right triangle. B squared is equal to A squared plus A squared, or 2A squared. So substituting 4R for B squared, we get 16R squared equals 2A squared, or A is equal to square root of 8 times R. Remember this, and this. So simple cubic unit cell, A is equal to 2R. Body-centered cubic, A is equal to 4R over the square root of 3. And face-centered cubic unit cell, A is equal to square root of 8R. So now we can do some stuff with that. So I'm telling you that calcium metal crystallizes in a face-centered cubic unit cell. FCC is face-centered cubic unit cell. The length of the edges in calcium's unit cell are 558.84 picometers. Let's calculate the radius of an atom in angstroms. Remember, an angstrom is 1 times 10 to the minus 10th meters. Picometer is 1 times 10 to the minus 12th meters. And then we're also going to calculate the density of calcium in grams per cubic centimeter. So let's do the first part. Here, all we're doing is plugging into the formula. So A is equal to square root of 8R for face-centered cubic, or R is equal to A over square root of 8. So we put A square root of 8 and get the answer. But that's in picometers. We want it in angstroms. So we can do it like this way. You can take the picometers, and in 1 meter, there's 10 to the 10th angstroms, and there's also 10 to the 12th picometers, so we get this ratio here. And we get our answer, 1.9758 angstroms. That's the radius of a unit cell, of a radius of the calcium atom. Now, the density, okay, has two parts, mass and volume. So the mass of a unit cell, okay, if we take how much calcium weighs, its molar mass, and then divide by Avogadro's number to get the mass of one atom, and you got to be careful to take this into account. Remember, in a face-centered cubic, there's 4 atoms per unit cell. So the molar mass of calcium divided by Avogadro's number times 4 atoms per cell gives us how many grams in a unit cell of calcium. So this many grams right here. Now the volume of that cube is just the length of an edge cubed. Well, the length of the edge was 558.84 times 10 to the minus 12 meters. See, what I've done here is I've just replaced pico with what it means, times 10 to the minus 12. I'm not worried about putting the decimal point over here or anything. This will give me the right answer. And we also know that there's 100 centimeters in a meter, so we can see that the length of the edge is this many times 10 to the minus 8 centimeters, 5.5884 times 10 to the minus 8 centimeters. And the volume is just that cubed, which is this number right here. To get the density, take the mass divided by the volume. And then we get 1.525 grams per cubic centimeter.